The point of this video is to code some rotational kinematics. And you might think it's exactly the same as translational kinematics, but some of the commands are a little bit different. We have to think a little bit. So I think it's worth showing you some things on that. So let's get into it. So to save some time, I hopefully in the links to the in the comments below the video, I'll try to put a link to some starter code so you don't have to do all of this from scratch. So look for that. So there should be, this is just drawing some stuff. This is setting some initial parameters. Maybe take a second to look at that. So obviously we need to convert to radians. So we're going to do that. And then omega is angular velocity. And then alpha is going to be angular acceleration. And you probably are familiar with the fact that technically we've got to be careful whether or not we could treat these as vectors or not. And it suffices to say that for a simple example where we're talking about rotation in a single plane and we're not doing multiple rotations about different axes, it is okay in this unusual case to treat these omega and things as vectors. And so I just want you to be a little bit careful to think about that. But for now, we're restricting ourselves to rotation in a single plane. So then it is okay to treat these as vectors here. All right. Some coordinate systems, that's great. Now, right around here, I think is where the starter code drops out. So I'm going to create a pivot. That's just a sphere. Okay, so that's obviously just a pivot point so that I have something visual to see. That's not really doing much. And then here I have a rod. And now, okay, notice I start with this rod. The left end is at the pivot. So one end of the rod is connected to the pivot. And then this axis says it's a rod of length 1, and it's directed along the x-axis. Now, if you recall up here, this theta is going to be the initial angle. So this is actually, I suppose I could have called it theta initial or something, but for right now, I want the initial angle to actually be 30 degrees. So how do I accommodate that? Right? Okay, so let's take a look. Somewhere in here, I'll do that. Oh, wait. So I did something else. I also drew a bug somewhere on the rod. So notice the bug is just going to be a sphere, which is located at the rod's position, which again, the rod's position is the same as the pivot position. And then we're going to add in, essentially this bug has been shifted distance bug R out from the pivot point. So it's basically, you got a 1 meter rod and this bug is sitting 0.6 meters out from there. And it's again, this is just some cosmetic stuff to make it look pretty when it moves. Next, let's take a look at this. I guess I did this thing a little bit out of order here, but looking at this, I want to draw an arrow representing the bug's velocity. All right, so this is kind of tricky here. I haven't forgotten about rotating the rod yet. Sorry, my code's out of order. But yeah, so I wanted to first figure out, I want to draw a vector here representing the bug's velocity. There are other ways to do it. This is how I thought to do it. Omega times the rotation axis is a vector. Now, if you recall, somewhere up here, we specified the rotation axis was in the z-hat, I believe. Come on. Oh my gosh, this is lagging here. There it is. There's the rotation axis. So notice the rotation axis is a vector that is 1 unit long in the z direction. So if I come back down to here, what does this omega vector mean? Well, it has rate omega. So the omega vector has size omega in the k-hat. So that's a fancy way of saying that right here. All right. So now, great. Now, what does that mean? Okay. So in this case, I'm kind of looking at, I'm going to go like this just to kind of get a feeling for it. Well, actually, let's do it like this. So we're looking at the same thing. Oh, you don't need all this. Let's get rid of that. All right, so let's say we have our rod right here. It's 1 meter long. We've placed a bug out here at some spot, about 2/3 of the way out. So there's our bug. Now we're saying this thing is going to have some angular rate of rotation this way, right? Well, that's omega in the k-hat. Notice my thumb is pointing out of the page. So omega in the k-hat describes curling this way. I take my right hand, I align the thumb of my right hand with the axis of rotation, in this case, k-hat. So it's going to curl this way. So this is going to be omega. All right, let's get back in there. So that's all this is. And now I'm saying that the bug's velocity is this unusual looking cross product. Whoa, let's think this through. This is omega vector cross the bug's position minus the pivot position. Now here, the pivot position is basically 0, 0, 0, but I think it's worth noting that this is, if I could write it this way, this would be R initial, and this could be R final. It's essentially like a delta R from the pivot to the point that we care about. And that's going to be a very common theme in chapter 10. We're always going from the pivot or the initial point to the point that we care about. All right. So going back to our whiteboard here. Well, this would be from the pivot to the point that we care about. And so if I just called that R with no subscripts for right now, right, we're doing, and let's see, what did I say? I think it was omega. Omega is out of the page, cross R, notice that points up. So again, this looks a little bit funny, but if I write it, remember we have omega in the k-hat crossed with, in this case, I think it was bug R, or so basically some distance in the I-hat for this one particular case, right? That would be k-hat, point your right hand. It's hard for me to get there with this angle. Point my right hand out of the page, align it with the first vector, curl to the second, that goes up. And so what I'm saying here is that the velocity is represented by that. That's the direction this thing is moving. So that's why this is a little bit trickier than translational kinematics. We have to think a lot about what these vectors mean to get a good visual representation with the minimum amount of coding. All right, so let's go back into here now and see if this makes sense. So that's this line of code. This is just a scale arrow. So what does this mean? If I try and draw the bug velocity full size, it's going to be huge. So what I did is I just played around with this number. You could have typed in 0.1 or whatever you want here. But the idea is this number is simply used to keep the arrow size under control. And notice, instead of making the arrow the size of the velocity, it's the velocity scaled down by some amount. All right. Whew. Next, this, finally I get to it. This is the piece of code that tells you how to rotate something. So if I take this rod and I rotate it, I choose an angle. Well, the angle we wanted was 30 degrees. Okay, the axis of rotation, actually the default, I believe, is the k-hat. But anyways, I chose to set this. And in this case, there's the origin. So you could set the axis and about which point. So you could actually fully control the rotation this way. You say about which point and about which axis and about which angle. So that's cool. And notice I did this for both the rod and the bug here. All right. So when we go into here, I'm going to write a simulation speed and some parameters here. So these are just kind of your standard tricks. And since we're at it here, let's think about this. If you knew the average period of something, right, we know that's 2 pi over omega, you could actually do a quick calculation. And as long as your time increment is less than, say, 100 times smaller than the minimum period, we expect this should be pretty accurate. So if you're wondering what value of dt should I use, we always just kind of play around with it. You could actually do a short calculation to figure out a good value for dt. And that might save you some time searching around, but okay, whatever. In this case, we're going to be changing things up, so let's not mess with it too much. Similarly, if you want something to be smooth to the eye, we'd probably want to go at least have a dt under 0.03 seconds. So because they have a refresh rate for your eye can see about 30 frames per second. So notice we should actually be able to see this a little bit. Maybe I'll even up this to 0.3. So we should see this happening quite a bit. Oh yeah, let's just say 0.2. Let's do that. All right, and now let's go into this. We've got our time set. We've got our initial angle change is 0, and let's go into here and see this. Okay, this just allows us to control the rate. Cool. Omega plus equals alpha dt, right? That's just the kinematics equation that we know. We know here that alpha vector equals d omega dt. Now, we could also just do this as a scalar in this case, which I believe is what I was working on here. I think omega and alpha were both scalars for us, since we're just doing this rotation in a single direction. And then here, I chose to do this slightly differently than before. So look carefully here. So you might say, well, why don't I just do delta theta? Oops, sorry. Why don't I just do omega equals delta theta over delta t? And then why don't I just say that omega final equals omega initial plus, what is this? Whoops, sorry about that. Why don't I just say, let me clear that out. I meant to say theta there and I wrote omega. Why don't I just say theta final is equal to plus equals omega dt, and just do the same thing? Well, you'll see why in just a minute. First, I want to get d theta, and that's the whole reason I had to do this up here, initialize it. So I want to get this small amount of angle because that's the amount of angle I need to use in the rotation equation. I don't just need the new value of theta, I also need the change amount so that I can rotate everything by the appropriate amount. All right, so when I go into here, notice what I'm going to do is I'm going to rotate the rod about this angle, and then I'm going to rotate the bug about that new angle, and then let's see here. We already have our new value of omega. Cool. So then I don't need to get the value of theta, right? I got the value of d theta and use that to update the positions of everything on the screen. Obviously, you could add another line of code that does give you a value of theta and make plots of that. That would be very useful. That'll probably be on the quiz if I remember to ask it. All right, now check this out. I again go in here and I get the new value of bug velocity. Notice I update the arrow's position to be on there. And then I also do this new, I get the new direction the velocity should point and scale it down. Okay, got it. Then I increment time. Okay, so finally we made it through all this code. Let's run it and see what it looks like. So hopefully you can see that going. It's slowing down, and at some point it reverses direction, and it goes the other way. And notice the velocity arrow is correctly updating. So that's the first step. Some side notes. There's some different functions you could use. Like you could use the group function. If you group them, you could actually group the rod and the bug, and you could look through the help file for that. The reason I didn't choose to do that was when you group them, I believe the tail function, the leave trail function doesn't make sense anymore or something like that. So you may choose to group them, but then you can't see the trail. And are there other ways to do this? Sure. And could I maybe have been a little bit more efficient? Yes. But I think this gets the idea across pretty well, and it leaves us